Hello friends, welcome to our YouTube learning channel Accurate ASME ISO. I think this video was long awaited by the industry. There would hardly a manufacturing industry exist where no challenge is found for concentricity measurements. When I talk of industry, I mean industries across the globe. I am sure that after seeing of this full video, there would hardly be any challenge or questions remain to ask. Still, in case of any specific query, please comment in the comment box. Please do not forget to subscribe the channel and share. So let us begin now. What is the objective of this video? The objective is why concentricity is a major inspection challenge in the industry when measuring on CMM as well as conventional measurement. In this presentation, let us see how to improve the repeatability of the measurement, reproducibility, and correlation of the results. The correlation of the result means the measurement is done at one place, one machine by one operator should be matched with another place, another machine by another operator or any of the change. Improvements are suggested through applying geometry controls on datum and features. Improving correct CMM programming methods. There are certain research available in the industries which we would take those as a reference. In the given drawing, concentricity of the cylinder is specified. With respect to the datum cylinder A, the tolerance given is 0.1 mm with cylinder tolerance zone. Let us do interpretation of the drawing requirement. The axis of the datum cylinder is extended up to the end of tolerance feature. Here, tolerance feature is the smaller diameter cylinder. Around the axis, a diametrical tolerance zone of diameter 0.1 mm is created. This tolerance zone is for the concentricity control. It means all the median points of the tolerance cylinder should lie inside the diametrical tolerance zone. Following animation represent the exact interpretation of concentricity tolerance evaluation. The datum cylinder is measured and the datum axis extended to infinite length as mathematics. After that, on the actual tolerance feature, a cylinder or number of circles are measured. The database stores the location of all the center points of the circles or the center axis if measured as cylinder. Around the datum axis, a diametrical tolerance zone is created. In this given condition, all the center points of the circles lies inside the diametrical tolerance zone, and therefore it is said that the concentricity of the given cylinder is well within the tolerance zone. The given case shows that datum cylinder and tolerance cylinder are located very closely. There is no separation distance between them. In the given condition of manufactured part as shown, the actual datum cylinder has got a form error like cylindricity or straightness error, because of which the actual axis produced is like this. This is slightly inclined to the nominal axis. The measurement of the tolerance cylinder is same as previous condition. In this condition, still concentricity is acceptable since all the points are well within the diametrical tolerance zone. Now, suppose the tolerance cylinder is not immediately connected to the datum cylinder, but it is far from it. This means there is separation distance between datum cylinder and tolerance cylinder. All other actual conditions of form and location remain same except the separation distance as shown. To calculate the concentricity, the datum axis is extended to reach the tolerance cylinder. It is now easily be understood that the datum axis will be projected at the constant angle or inclination. This small inclination is enlarged when it reaches to the tolerance cylinder. Around the datum axis, the same cylindrical tolerance zone is built. In this condition, concentricity calculated is out of tolerance value. The reason remains as simple that the tolerance cylinder is placed at farthest distance and mathematical calculations produced the more error. Rule of proportionality. This slide will help us to draw some conclusions. There is direct relation between the datum cylinder length and the separation distance between datum and tolerance cylinder. For example, if datum cylinder length is L millimeter and separation distance is 3 times, that is 3L, then the inclination error at datum cylinder also propagate 3 times. Therefore, we can say that as the separation distance between the feature increases, the error of measurement also increases in the proportion. What should be ratio of feature distance to datum length? Author Mr. Robert writes in his book Measuring Strategy that the quality of the datum measurement has a direct influence on the quality of the measuring results. The following example illustrates the problem of short datum features on a long part. Form deviations on a short datum feature have a disproportional effect on the position and orientation of a measured feature. They pivot the coordinate system like a lever. Here, length of datum A, that is cylinder length L1, is very short as shown in the figure. The separation distance from datum cylinder to tolerance cylinder is L2. This distance L2 is many times larger or greater than the length L1. Now, by the rule of proportionality, a small deviation of datum cylinder increases dramatically at the tolerance cylinder. And therefore, author recommends that the ratio of feature distance to datum length should be equal or less than 3 to increase the reliability in the measurement. If the ratio is not less than or equal to 3. Then there is a new approach suggested for the effectiveness of coaxiality tolerance verification. There is a research study published at National Technical University of Athens, Greece, in the Department of Mechanical Design and Control System, School of Mechanical Engineering. A complete research paper is available on the internet and the link is provided here for your reference. The abstract of the paper is one of the most complex tasks that are carried out by coordinate measuring machines is the verification of coaxial deviation of cylindrical features. The paper addresses the difficulties met in the evaluation of coaxiality tolerances. A set of criteria based on current GD&T standards and industrial engineering practice are introduced in order to safeguard the effectiveness of the coaxiality tolerance verification. The proposed criteria, along with the novel CMM measurement strategies for the practical verification of coaxial deviations that are presented, can be easily implemented in CAD or CMM environments. The functionality of the approach is illustrated through an application example. The conclusion of the research is as shown in the figure B. In the figure A, coaxiality tolerance of right hand side cylinder is given T with reference to datum cylinder A. The figure A drawing is suggested to modify like figure B. In this drawing, a common datum A-B is created passing through both RHS and LHS cylinders. With taking A-B as a common datum, coaxiality of individual cylinder is measured. Individual means concentricity on the left hand side cylinder and on right hand side cylinder. For evaluation of coaxiality tolerance for both the cylinders, tolerance is assigned half of the original tolerance. It means the original tolerance is T and now it got modified T by 2. The content of this slide is referred from the cookbook of a well-known CMM manufacturer. This booklet is available on the internet in the public domain and link for the same is given here. This book also suggested the same method of coaxiality measurement as we discussed in the previous slides. Let us take a real case study of coaxiality measurement. The measurement is shown in real time by conventional method and the CMM method. In this video, coaxiality of one end cylinder is measured taking another cylinder as a datum. The measurement is being carried out with a plunger type dial gauge. The highest point at the location 1 is made 0. The reading taken at the location 2 is measured 10 micrometers. The variation is because of the part is not physically aligned. Without the disturbing, at the other end cylinder measurement observed is 80 microns. With the best effort, the variation of location 1 and 2 is minimized by truing the component or physically aligned. After the alignment, the difference remained is of 2 microns. The calculation is done like difference of 7 micron at location 2 and 5 micron at location 1, and the absolute difference between them is of 2 micrometer. In the same setup, the observation noted at the location 3, that means cylinder at the other end, with the aligned condition is 28 microns and on negative direction. To summarize, all three readings are shown in the first column. If we remove the common error of 5 microns, then for the 2 micron of the taper of the datum axis, the tolerance cylinder measured is minus 32 microns. Let us now call both the conditions together. The first one is when there was error of 10 microns at datum cylinder, the concentricity measured was plus 80 microns. After that, when the error was reduced to 2 microns at datum cylinder, then concentricity observed was minus 32 microns. The analysis of the data says that if the error at the datum reduces by 8 microns, the concentricity error changes from plus 80 microns to minus 32 microns, and the absolute variation observed is minus 112 micrometers. This demonstrates that how sensitivity reflects in the measurement of the concentricity. When there is very short length cylinder treated as a datum and the tolerance cylinder is located at very far distance. So, finally, what will be the solution? Of course, yes. All the research studies and international best practices suggested that the only solution is to modify the drawing. The modifications are assign concentricity to both the cylinders, that is point number 1. Point number 2 is concentricity tolerance zones divided equally between both the cylinders. For example, if there is a value T in the original tolerance, then for both the cylinders it would be T by 2. And finally, point number 3 is both the concentricity is measured by a common datum A-B. At the end of this video, let us have a summary and conclusions. Measuring challenges. When coaxial features are located with separated distance between them, projection error of datum is increased. Rule of proportionality. To have a reliable measurement result, the ratio of feature distance to datum feature length should be equal or less than 3. According to the international standard ASME Y 14.5 2018, clause number 7.8 datum features make a statement A datum feature is selected on the basis of its functional relationship to the tolerance feature and the requirement of the design. To ensure proper assembly, corresponding interfacing features of mating parts should be selected as datum features. However, a datum feature should be accessible on the part and of sufficient size to permit its use. Best industrial practices. If the ratio become more than 3, then measure datum and tolerance feature as individual cylinder, or measure more circles on datum and tolerance features. Maybe 3 circles on datum cylinder and 3 circles on tolerance cylinder. Construct a line passing between two measured cylinders. Or if circles are measured, then line passing through all the circles measured at both end features. Now measure concentricity of cylinders or circles individually with respect to a constructed line that is a common datum. The tolerance of the both concentricity should be half of the specified tolerance in the original drawing. Hope that you like this video. Please do not forget to subscribe the channel and share it to others. For training inquiry, please find the contact details on the slide. Thank you friends. Take care. Bye for this time. See you soon for the next video. Thank you once again.